Hi, this is Rachel Davis, and we're going to be doing Chapter 4 from the Burdge textbook, which is Solutions, Reactions that take place in aqueous solutions. Aqueous meaning solutions that are in water. So first we're going to talk about properties, and then we're going to look at those reactions. The first property I'm going to talk about is whether or not the solution is an electrolyte. So the solutions can be strong electrolytes, weak electrolytes, or non-electrolytes. And this handy little flow chart here that is in your textbook, this is on page 133 of the 4th edition, will help you guide you through whether or not a solution is an electrolyte. So what is an electrolyte? Water by itself cannot conduct electricity. And to prove this to you, I have just a little beaker right here of distilled water, just plain distilled water. And here I have a light bulb. Now this light bulb is attached to a battery, so it should be lighting up, except that right here, the electrodes have this gap between them. If they were connected, then it would light up. But that gap right there, if water could conduct electricity, electricity would be able to run through that gap and connect and allow the light to light up by connecting the circuit, and nothing happens. But if I pick a solution that is an electrolyte, so here I have some potassium iodide. Looks like water, looks just clear, like there's nothing there, but it has something dissolved in it. It has potassium ions and iodide ions. Now when I put that solution in there, see how it lights up? Because that solution is an electrolyte and it is able to conduct electricity through it because of the ions. So you have to have a solution that will produce ions in water. So off of this flow chart here, we're going to do this with a couple of examples here and determine whether or not these things are going to be electrolytes or not. The way these flow charts work is you're going to ask yourself a series of questions. The first question is the compound ionic or molecular? So in chapter 2, we learned how to distinguish between ionic compounds and molecular compounds. Ionic have two parts, a cation, which is positively charged, and an anion, which is negatively charged. The cation is always either a metal or NH4, ammonium. So looking at this first compound, we have C6H12O6, that's glucose. There are no metals, there is no ammonium, so that would be molecular. So the next question, if I say it's molecular, is it an acid, base, or neither? Now, C6H12O6 is not an acid nor a base. We'll talk a little bit about how can you tell when it is. So if it's neither, then the compound is here. It's a non-electrolyte. So you would say this is non-electrolyte. Next example we have here is HF. HF is also molecular. There's no metals. There's no ammonium. So down here, the next question, acid, base, or neither. HF starts with hydrogen. And if hydrogen is written in the start of the formula, that's a big hint that it's probably an acid. There's some exceptions to that rule, the notable being H2O. Water starts with the hydrogen, but it's not an acid. Also, hydrogen peroxide, H2O2, starts with hydrogen, but is not an acid. But most other compounds you're going to see in this class, if it starts with hydrogen, is going to be an acid. So this is an acid. So we're down here. Yes, we are an acid. We're going to drop to the bottom question. Is it one of the 7 strong acids listed in table 4.1? If all of the acids, only 7 of them are what we consider strong acids, meaning that they dissociate completely in solution. Weak acids only ionize a little bit, so you only get a little bit of ions. HF, hydrofluoric acid, is not one of those 7 strong acids. Things like HCl, HBr are, but HF is not. So it would be no, not on the table, not a strong acid, therefore it's here, it's a weak electrolyte. Next one, KOH. This is potassium hydroxide. Potassium is a metal, hydroxide is a polyatomic ion. So this is an ionic compound. So we're going to go over here. It's a compound ionic molecular. It's ionic, then it's automatically a strong electrolyte, assuming it's soluble. And for these examples, we're assuming they're all soluble. So that's strong electrolyte because it's soluble. Next we have NH3, which is ammonia. It is molecular. So we're down here. Acid, base, or neither. Ammonia is molecular, or is a base. So if it's a base and it's molecular, it's a weak electrolyte. So this one is weak. So this is when people try and jump ahead. They try and jump to say, oh, it's a base, it's automatically a weak electrolyte. And here's the trick here. Potassium hydroxide is also a base. but it was a strong electrolyte. And that's because people jumped to the second question without answering the first question first. Answer the first question first. KOH is a strong electrolyte because it's ionic. Bases are only weak electrolytes if they are already molecular before you identify them as a base. So only molecular bases are weak electrolytes. Ionic bases are strong electrolytes. Next one, H2O2, I kind of already gave you the answer for that one. That is hydrogen peroxide. It's molecular, it's neither acid nor base, so it is a non-electrolyte. The last example here is HNO3. So NO3 is nitrate, so the acid formed from it must be nitric acid. So following down, it is molecular, it is an acid, and if you check table 4.1, HNO3 is one of the 7 strong acids, so yes it is. So therefore it is a strong electrolyte. This identification is going to be important later on when we're writing out our ionic and net ionic equations, because in an ionic equation, only strong electrolytes are written as their individual ions, because only strong electrolytes completely break apart in solution. So of these, only potassium hydroxide or nitric acid would be written as separate ions in solution. The other ones would be left in the ionic equation as just the molecular form. All right, so moving on. Next thing we can talk about with solutions is whether or not they are soluble. Some compounds are soluble in solutions, some are not. So in the last example, we were automatically assuming they were soluble, but they might not be soluble. Some ionic compounds are not soluble. And this table, this is table 4.2 in your textbook, will help you to determine whether or not an ionic compound is soluble. So the way this works is the first column are the rules, and if there are any exceptions to that rule, they are listed in the second column. So first look for a rule that applies, and then check to see if there are exceptions. Don't jump to the exceptions and say, oh, it has silver, therefore it's insoluble. That's only an exception to this rule if you've already determined that you are that rule. So let's look at a couple of examples here. Let's say I've got ammonium hydroxide. So ammonium is a polyatomic cation, hydroxide is a polyatomic anion. If I'm looking down the rules, the very first rule here says compounds containing an alkali metal cation, that's everything in group 1 of the periodic table, or the ammonium ion, NH4, are listed as water soluble, and there are no exceptions. Because I contain ammonium, I am soluble, there's no exceptions. Doesn't matter what the rest of the compound is. You do not have to get both parts of this to match to a rule. Only one part needs to match to a rule to determine that it's soluble. If I had, say, BR2. So this is lead to bromide, lead to bromide. There are no rules for lead, but there is a rule for bromide right here, and it says bromide is water soluble. But that's one of the rules that have exceptions, so we need to go over here and check to see if that's one of the exceptions. And sure enough, lead 2 is one of the exceptions, which means this would actually be insoluble. Most compounds, their solubility can be determined from this table. If you have a compound that you cannot find any rule that would apply for this table, then it's generally safe to assume it's insoluble. For example, if you had barium fluoride, BaF2. There are no rules here for barium. There are no rules here for fluoride. Therefore, assume it is insoluble. And that's how to determine whether or not a compound is soluble or insoluble, which is the other piece of information we need when we are writing out the molecular net ionic equations. So let's look at those molecular and net ionic equations next. So for the molecular equations, first we're going to focus on the double displacement reactions. So double displacement reactions are when two ionic compounds react in aqueous solution. So what this looks like is I have two ionic compounds. So each one has a cation. It could be a monatomic cation, like sodium or magnesium or lead, or it could be the polyatomic cation ammonium, NH4. And then some anion, again, this could be monatomic, bromide, chloride, some nonmetal, or it could be polyatomic, sulfate, nitrate. And this reacts with another ionic compound that also contains a cation and anion. And in solution, what they're going to do is switch partners. So this positively charged cation is not going to be interested in the other cation, right? Same charges repel, opposite charges attract. So it's going to be attracted to that negative ion on the other compound. So A is going to jump to D. So I'm going to have a reaction between A and D. And C is going to jump to B. So I'm going to have C and B. Remember, we always write the cation, the positively charged ion, first in the compound. So here are our products of the reaction. At this point in time, we need to make sure it is balanced and determine whether or not they are soluble. So I'm going to write up an example here that I've got the solutions here that I can show you. And that is if I had potassium iodide, and this is a solution. So that is the potassium iodide solution that I showed you earlier with the light bulb. And lead 2 nitrate. So lead 2 nitrate has lead with a 2 plus charge. So since nitrate has only 1 minus charge, I need 2 of them. And they are going to react. Now because the screen's kind of short, I'm going to have to do this on this bottom here. Let me go ahead and switch colors and show you what our products are going to be. So when we have these as compounds, we do not show the charges, but they are still charged, the individual cation and anion. Potassium is a group 1A metal, so it has a 1 plus charge. So I'm just going to make a little note of that up here, that is potassium plus. Iodide is a group 7 nonmetal, therefore it is a 1 minus charge. That's technically I with a minus. Lead, this is lead 2, so it's PB2. And if you didn't know that if it was lead 2, nitrate, NO3, is a polyatomic ion, and it has a 1 minus charge according to the polyatomic ion table. So if I have 2 of these, I have 2 negative charges, so my lead must be lead 2 plus. So potassium is going to leave iodide and is going to be attracted to nitrate. So our first product is going to be potassium and nitrate. Because this is plus 1 and that is minus 1, they would go together in a 1-to-1 ratio. So potassium plus and nitrate minus. Now once again, once we make a compound, we're actually going to get rid of those charges. So let me erase those charges because they have now canceled each other out. And I'm just going to put a placeholder for the state of matter and determine whether or not it's soluble next. Second compound, I have lead 2 plus and I have I minus. So because lead has 2 positive charges, iodide has only 1 negative, it's going to take 2 iodides to cancel out that 2 positives. So my second compound is going to be lead I2 in order to cancel out the charges. Now I need to see whether or not these are soluble. If they're soluble, they stay aqueous. If they're insoluble, they change to a solid. So the first one we have is potassium nitrate. Let's go back and look at our rules. So, potassium, right there. Compounds containing potassium are water soluble with no exception. And actually, it's doubly soluble because nitrate is also a rule with no exception. So that one is definitely soluble. So I'm going to put aqueous here. Next one is lead iodide. So looking at our rules here, lead iodide, I don't have a rule for lead, but I have a rule for iodine. It says that it is soluble, but there lead 2 is one of the exceptions, so it's going to be insoluble. So I'm going to change that to a solid. Last step of this molecular equation is making sure everything is balanced. So going back to what we learned in chapter 3 about balancing equations. If I have 1 iodide on the reactant side, but 2 on the product side, I'm going to need to put a 2 out front here. Now, if I have 2 nitrates on the reactant side and just 1 out here, I'm going to need a 2 there. Now, I started with 2 potassiums, ended with 2 potassiums. Started with 2 iodides, ended with 2 iodides. Started with one lead, ended with one lead. Started with two nitrates, ended with two nitrates. So now this is our balanced molecular equation. Because this produced a solid, now they don't always, but in this case it produced a solid, that's what we call a precipitation reaction. Precipitation reactions are those that produce a solid when two aqueous solutions are combined. So I actually have these that I'm going to show you. Again, there is our potassium iodide solution, and now I have here our lead nitrate. Let me actually switch them so they're in the order that they're up on the screen. Potassium iodide and lead nitrate, and I'm going to mix those two together and show you exactly what happens. A similar reaction to this is actually in your textbook. We mix them together, boom, something happens. Yes, there's a color change is the obvious thing, but something else happened. It's no longer transparent. It's no longer transparent because it's not that it changed color, it's that it formed a solid compound. That yellow color that is now blocking light through because it's actually a solid is going to be our lead iodide here. Now, right now it's kind of like a slurry. Right now, all of that solid is just kind of clouding up, but if you let this sit, it's going to all come down and settle down to the bottom. So here's one I did about 5 minutes before I started the video. Same reaction, and if you'll look here, it's starting to settle down to the bottom, and the solids are mostly down there at the bottom of the test tube. So this is what a precipitation reaction looks like. They don't always have a color change, but they will produce a solid that will make the solution cloudy, and eventually, given enough time, or if you put it in a centrifuge, that solid will all settle down to the bottom. So that is the molecular equation for this. Now let's go ahead and do the ionic equation and the net ionic equation. So I've just rewritten so we have space up here, our molecular equation. The ionic equation takes anything that is a strong electrolyte and breaks it apart into the individual ions. So strong electrolytes, to recap, are either soluble ionic compounds or strong acids. Those are the two things that get broken apart in a ionic equation. So first of all, we have potassium iodide here. That is an ionic compound and it is soluble, so that will break apart into its individual ions. To know what the charges on those ions are, you can go back to chapter 2, look at the periodic table. Everything group 1 is going to be a 1 plus, group 2 is going to be a 2 plus, everything group 7 is going to be a 1 minus, or if it's a polyatomic ion, whatever the polyatomic ion charge is on the table of polyatomic ions. So this 2 in front says that I have 2 of the entire compound, 2 potassium ion compounds. So when I break them apart, that is going to give me 2 potassiums and 2 iodides. Potassiums again are +1, iodides are minus, so that 2 gets distributed there. Now everything needs a state of matter. These are aqueous because they're dissolved in water. So there is my first compound broken apart into its ions. Next I have lead nitrate. That's also ionic and also soluble, so it's also going to break apart. So this is lead 2 plus, that's aqueous, and then the nitrate, NO3 minus, that's aqueous. And what about this 2 down here? What that means is that my lead has 2 nitrates on it. So if we thought about it like visually, here's my lead ion, 2 plus, and then it's got, let me change the colors. It's got 2 nitrate ions on it, NO3, NO3. So that's what it is. Now, what this is saying is that because that's a strong electrolyte, because it's ionic, because it's molecular, this is going to break apart in. So as these things break apart here, and they're going to float away from each other, I'm going to be left with a lead 2 plus, and I'm going to be left with 2 NO3s. So I'm going to show that by writing a 2 in front here. I have 2 nitrates. So that's it for my reactant side. Now let's look at the product side. Let me get rid of these. Now on the product side, potassium nitrate is still ionic and it is still aqueous, so that is still a strong electrolyte. So I'm going to get 2 potassium ions, so 2 K pluses, aqueous, and 2 nitrates. Remember, the 2 distributes to both things, so I get 2 nitrates there. Now the last part of this equation is the lead iodide. Now lead iodide is a solid. It can't break apart in solution because it didn't even dissolve in the solution. That is a non-electrolyte. It didn't even dissolve, so it can't dissociate into ions. So because of that, in the ionic equation, we're just going to leave it as lead iodide with a solid. Now, if we carried all of our prefixes down correctly, then we're still going to be balanced. 2 potassiums, 2 potassiums, and so on. So double check to make sure everything is still balanced. It should be if you did this correctly. So here's our molecular equation and our ionic equation. The last one is the net ionic equation. So the net ionic equation, we're going to cancel out what's called spectator ions. Spectator ions are those ions that occur on both sides of the equation. So anything that just didn't react, it was floating around in the beginning of the solution, it was floating around in the end, and it didn't technically react with anything. So in this case here, let's look. I start with 2 potassium plus aqueous ions. In the end, I've still got 2 potassium plus aqueous ions floating around in solution. So I'm just going to cancel them out. Same thing with the nitrate. I have 2 nitrates floating around and 2 nitrates floating around. And so those also did not change. Those are also spectators. The iodides, those change. The lead, that changed, that reacted, so that's what's left over. So our final net ionic equation is going to be the 2I minus and the lead 2 plus. And that is all for the reactant side. On the product side, we have lead iodide. Why did it just change color? There you go. Lead iodide solid. And that is our net ionic equation. Make sure everything has a state of matter, and that when it's a compound, you do not show charges, but if it's an ion sitting by itself, it does have a charge. So that is writing out, in this case, it was a precipitation reaction. Now, in some cases, you may not have any spectator ions. In that case, your net ionic equation is going to look just like your ionic equation. In other cases, this happens if, say, both of these ended up being aqueous, and the double displacement ended up producing 2 aqueous compounds, then everything would end up canceling out and your net ionic equation would just say no reaction occurred. So the next kind of thing you can write a molecular ionic and net ionic equation for is an acid-base reaction. So that'll be in the next video.